SwayamPrabha. Digital India. Educated India.
So, if you recall, in the last class I just stopped with a brief introduction to root locus, right. So, we saw that the standard feedback block diagram is going to be in this form, right. So, that is what we have been studying, and we essentially know that the closed loop transfer function is y of s divided by r of s is going to be g of s divided by 1 plus g of s h of s, right. So, g of s being the forward path transfer function, h of s being the feedback path transfer function. Also please note that recall that g of s is going to be c of s times p of s, right. So, we can have the it's basically the product of the controller transfer function and the plant transfer function, right. Okay. So, now this equation is what is called as a closed loop characteristic equation, right. So, that is what is the name given to this equation. So, 1 plus g of s h of s equals 0 is the closed loop characteristic equation. Of course, 1 plus g of s h of s is what is called as a closed loop characteristic polynomial, right. And why is this important? Just to recap, the roots of the characteristic closed loop characteristic polynomial or the closed loop poles, right. So, that is why we are interested in this equation, right. So, this is where we what we have already looked at. So, if I rearrange the terms in this equation, I get g of s h of s to be equal to minus 1, since that s is a complex variable and g of s h of s is going to be a complex valued function of s, right. This immediately gives me two conditions, okay, that the magnitude of g of s h of s should be equal to 1 and the phase of g of s h of s should be an odd multiple of 180 degrees, right. So, those are the two conditions that we get. So, okay. So, this one is what is called as the magnitude condition, okay. This is what is called as the angle or the phase condition, right. So, any value of s that satisfies these two conditions is a closed loop pole, right. So, that is essentially something that we discussed, right. So, once again I am just recapping what we did in the last class before continuing from there, okay. And what we also discussed is that, like, typically the open loop transfer function is expressed as or can be expressed as the following. Okay. Suppose if we are able to express the open loop transfer function in this form, g of s h of s being some constant k times s plus z1, s plus z2 all the way till s plus zm divided by s plus p1, s plus p2 all the way till s plus pn, right. So, k being some what to say constant, right, real number, and minus z1 through minus zm are the open loop poles, right, minus p1 through minus pn are the open loop zeros, right. So, that is something which we already know. So, minus z1 minus z2 all the way till minus zm are the open loop zeros, or they are nothing but the zeros of the open loop transfer function. Minus p1 minus p2 all the way till minus pn are the open loop poles. Okay, so that's the terminology which we already know, right? Okay. Now the question that we want to ask is that, like, how would the closed loop poles change as k is varied, right? So the question is, how would the closed loop poles change as k is varied? Okay. So let us first consider the scenario where k is a non-negative scalar, right? So let us first consider the scenario when k is greater than or equal to 0. Okay. So of course, equal to 0, like, doesn't make sense, right? So of course, in practice it's going to be greater than 0. So but we are going to look at the limiting value of k tending to 0 and k tending to infinity. Okay, so that's what this means, right? So essentially we can immediately see that the closed loop characteristic equation is going to be in this form, right? So 1 plus k times s plus z1 till s plus zm divided by s plus p1 all the way till s plus pn is equal to 0. Okay, so that's what we are going to have. Now the question is, the root locus plot essentially gives us the locus of the closed loop poles as k is varied, right? So that's essentially the purpose of the root locus plot. Okay, so we are going to learn how to construct the root locus. Of course, in this exercise, like, I have already provided you with a handout. If you noticed in the course website, I have uploaded a file which details the list of steps involved in the construction of the root locus plot, right? So that's something which I have already uploaded. So please download and go through them. Okay, so I'm just going to list those steps. Like, I'm going to give you an intuitive understanding of those steps, okay, rather than proving each and every step, okay, or deriving each and every step. Okay, so that's going to be our focus here, right? Okay, so let's first thing to note is that the root locus will have n branches, right? So that's one point we need to notice, right? The root locus would have n branches. Why? Because there are going to be n closed loop poles, right? So this is an nth order system, there are n closed loop poles, so obviously the root locus would have n branches, right? So now the question arises, like, how do we plot these n branches in reality? Okay, and by and large we will see that we are going to use the angle condition to our advantage. Like, that's something which we are going to look at. Okay, before we go into this derivation, right, so, or this process, let me take a simple example. Okay, so let's say I take g of s h of s to be equal to, let's say, k divided by s plus 4 times s minus 1, let's say, like, just to convey the point, right? So k is some non-negative real number, right? And this is the open loop transfer function. Can happen, right? See, for example, how can we get this open loop transfer function? Let us say, like, I have a negative feedback system, okay, where the controller is a proportional controller. Okay, instead of kp I call it as k. Okay, it doesn't matter, right? The proportional gain I just call it as k. Let's say the plant transfer function, let us say, where 1 divided by s minus s plus 4 times s minus 1, okay, and suppose if I have unity feedback, that means h of s is going to be 1, you can immediately see that the open loop transfer function is going to be k divided by s plus 4 times s minus 1, right. So, that is what we are going to have. Okay. Now, if I look at the system, immediately we see that the value of n is going to be, what do you think is the value of n? 2, right. What is the value of m? Yes.
What is the meaning of locus of the closed loop?
Locus of the closed loop poles, sorry. Okay, thank you. Okay, I missed the word poles. Okay, so locus of the closed loop poles, sorry about that, thank you. Okay, so n is going to be 2 here, okay, m is going to be 0, okay, the open loop poles are at minus 4 and 1, okay, and there are no open loop zeros, correct, that is what we have here. Now, if I construct, like what we call as the S plane or the complex plane, okay, and then like see what happens. So, let us say I construct the S plane. Okay, the real axis, the imaginary axis, the origin. So, in this particular example, let us say I mark the 2 open loop poles, they are at let us say minus 4 and let us say plus 1, right. So, there are no open loop zeros here. Okay. So, let us say like I take some test point here, yes. Okay. So, let me put a what to say subscript t. Okay. So, S subscript t means like it indicates a test point, right. So, I can essentially take some test point on the test point in the what to say S plane, and I want to figure out whether like this lies on the root locus or not, right. So, question that we want to ask ourselves is that how do we determine if the test point ST lies on the root locus. Okay, so that's a question we are going to ask ourselves, right? So now, like if suppose if the test point lies on the root locus, like that test point should satisfy 2 conditions, right? What are they? Because that's what we figured out, right? So if any value of S has to be a closed loop pole, it has to satisfy the magnitude condition and the angle condition, right? Please note that once again we are checking the open loop transfer function, okay? That's one important feature of this method, right? Although we are interested in the closed loop poles, we are evaluating the open loop transfer function. Please keep that in mind, right? So, let us look at the typically we will shortly realize that by and large in this exercise the angle condition is the one which is going to be pretty helpful to us, right. So, let us figure out what is the phase of G of S H of S when it is at the test point, right. So, that is going to be the phase of k divided by St plus 4 times St minus 1, okay. So, that is going to be the phase, right. Now, from our what to say knowledge of complex variables, like so let us say like if I have products and ratios of complex variables, what can I tell about the what to say phase of the products and ratios. Let us say if I have product of 2 complex variables, right, what can I tell about their phase? They get added, right. So, if I have a ratio, they get subtracted, right. So, we are going to get the algebraic sum, right, of the phases, correct. So, this is going to give me phase of k minus phase of St plus 4 minus the phase of St minus 1, right. Do you agree? Okay. Now, like to begin with the parameter k is taken to be positive, right. So, what do you think is the phase of k? It is going to be 0 degrees, right, because k is going to lie somewhere on the positive real axis. See, how do we get the phase of a complex number? You draw a vector from the origin to the corresponding point, then you measure the angle that it makes with the positive real axis, in the counterclockwise direction, right? That you take it to be positive. Okay, so that's the convention, right? Is it not? Okay. Now, if I want to figure out the phase of ST plus 4, you know, like how would I do that? What is ST plus 4? See, I can write ST plus 4 as ST minus of minus 4. What is ST? The vector ST is going to be, oops, let me try to draw a straight line. Okay. Okay, the vector ST is going to be from the origin. Okay, it's not very straight, but you get the point, right? So, it is going to be from ST to the origin, right? So, this is the vector ST, right? What is the vector minus 4? The vector minus 4 is going to be from the origin to minus 4, right? So, what is going to be ST minus of minus 4? It is going to be a vector which starts from minus 4 and goes towards ST, okay? That is the vector. This is the vector ST minus of minus 4, right? So, what is the angle made by that with the negative positive real axis, right? With the direction of the positive real axis, it's going to be this, okay? So, let us say we call this as some theta 1, right? That is what it is, okay? So, then how can I get ST minus 1? Same philosophy, right? So, the vector 1 is going to be from 0 to 1. So, ST minus 1 is going to be from 1 towards ST, okay, the arrow pointing towards ST, right. So, the angle made by the vector ST minus 1 is going to be this theta 2, all right, that is what it is going to be, okay. So, of course, the angle contribution from K is 0, this is theta 1, this is theta 2. So, this is going to become minus of theta 1 minus theta 2. The question that we are going to ask ourselves is that, is this going to be an odd multiple of K? Okay. So, we will see that by and large the angle condition is used to plot their root locus, and the magnitude condition is typically used to get the value of K, the gain K that appears in the open loop transfer function at any given point on the root locus. Okay, that is how the thing works. You know, we will realize it as we do more examples. Okay. So, that is, I put a question mark because we want to ask ourselves the question, right. So, if I consider an arbitrary test point and if I have to evaluate that test condition, right. Now, if the test point satisfies this angle condition, then I can say that the test point ST is on the root locus. Okay. So, that is how we are going to evaluate root locus. Is it clear? Okay. Now, let us go to the steps involved in the construction of the root locus. Okay, any questions on this? Magnitude condition. So, typically what happens is that the root locus plot is, the steps involved in the root locus plot are generally constructed using the angle condition, okay. And once you get the plot, at any point on the locus, you know, like you can get the corresponding value of K using the magnitude condition. We will shortly see that, okay. Yeah, I have taken any arbitrary test point, okay. But of course, this is not how we will plot it, okay. We have a series of steps, okay, which helps us to plot by hand, all right. Yeah. Zeros, open loop. O dot L means open loop, okay. That is the abbreviation I am using for open loop. Closed loop I am using C dot L dot, okay. Yeah. Okay. So, anyway, in MATLAB you will have this command R locus, okay. Like, so if you look it up in MATLAB, so the command R locus is essentially used to plot the root locus, okay, of a given open loop transfer function, okay. So, now let us go to the document which I uploaded and then like see, I hope I have it here. Yes. And then like let's look at that. So let's go through the steps involved in constructing the root locus. So once again we are considering a closed loop negative feedback system whose characteristic equation is this, right? Whatever we have considered. So of course we shall consider the case when m is less than n, right? So that's very important, and k being a positive parameter, right? So that's a condition that we have started with. And we know that minus z1 minus zm through minus zm are the open loop zeros, and minus p1 through minus pn are the open loop poles. The root locus traces the evolution of the roots of this equation with variation in k, and as we discussed, the root locus will have n branches or curves. Okay. So suppose if you are given a particular open loop transfer function, how do you go about constructing the root locus? Okay, you just need to follow these steps. Okay, that's all there is to it. The first step is to locate the open loop zeros and poles in the complex plane. Okay, that is the first step. So note that each of the n curves in the root locus will start from an open loop pole for k equals 0. Out of these, m curves will terminate at an open loop 0 as k tends to infinity, and the remaining n minus m curves will go to infinity in the complex plane along asymptotes, okay, as k tends to infinity. Okay, so let's discuss this point, right? So what does this mean? And anyway, what I will do is that to better understand these steps, we will start constructing the root locus for the system. Okay, so that we work on this on these steps along with an example, right? So that's what I am going to do. So let's look at the first step, right? Step 1 is to locate the open loop poles and open loop zeros, right? So that's something which we have already done, but let me do it fresh. Okay, so let's say this is my S plane. Okay, the real axis and the imaginary axis. Okay, so this is the S plane. Okay, this is the origin. So let's say my open loop pole is at -4 and another one is at -1. Okay, so those are the two things that we need to worry about, right? So the open loop poles are at -4 and -4 and +1, right? Yeah. Okay, there are no open loop zeros. So now there will be two branches in the root locus, right? So because n is 2 here, right? So the root locus will have would have two branches. That's pretty obvious, right? So because anyway we have seen we can see immediately from the open loop transfer function that the order of the closed loop system is also going to be 1, right? Because what is going to be the open loop closed loop characteristic equation? The closed loop characteristic equation is going to be 1 plus k divided by s plus 4 times s minus 1 is equal to 0, all right? Okay. Now as k tends to 0, as k starts increasing from 0, each branch will start from an open loop pole. You know, like, why do you think that happens? So immediately you can rework this equation, right? I can rework it as s plus 4 times s minus 1 plus k equals 0. So now the answer is pretty obvious, right? You substitute k equals 0. What are the roots? -4 and +1. So you can immediately see that there will be n branches, in this case 2 branches, and each one of the 2 branches would start from an open loop pole at k equals 0, right? So we are going to have 2 branches starting from -4 and +1, okay, when k is equal to 0. Now the question is that when they start from -4 and +1, they are going to start like this, okay? Like I'm going to draw why they start like this. You tell me the answer, okay, and the justification as to why, okay? So the 2 branches of the root locus will start like this. So when the one branch which starts at -4 would go towards the right on the real axis, and the branch starting at +1 would go to the left on the real axis. What do you think are the reasons behind this? Branch means it's just a locus of the closed loop pole as you vary k. Let's say you keep on plugging different values of k. Obviously, you are going to get different values of S, right, in this closed loop characteristic equation. So, the root locus essentially gives you a graphical representation of that. Okay? So, because there are going to be two roots, right? Now, as you vary k from 0 to infinity, like how will those two roots evolve with k?
So you're telling like as we vary k from one value to other, then S will always have two solutions.
Two solutions, yeah.
So one solution is from branch 4 and another is from branch 4.
Yeah, one solution is from one of these branches, another from the other branch. Okay. Does it matter? No. See, what we are interested in is the solution itself, right? So you can call this as root 1 and root 2 or vice versa. No, that's your choice, right? So I'm asking you a question, does it matter? We need to think through, right? You also think through, okay? Does the order matter, right? So they're just two solutions, right? See, if you think about it, even the open loop pole, like you can write it as -4 and 1 or 1 and -4. Do you think the order matters in this case? Let's think about it, okay? And if it matters, let's discuss why, right? Okay. So, so two branches start off like this, right? Why would you think they? I have drawn them like this. So I think throughout this discussion, I'm going to give you some logical arguments, right, rather than proving it mathematically. Okay, that's going to be the thought process. And for those who are mathematically inclined, I would ask you to prove them. Okay. As voluntarily, okay, not part of, you won't be tested on those derivations, right? Yeah. So please note that -4 is on the real axis. Can a branch go anywhere else other than on the real axis? Please note what each branch indicates. Each branch tells me the root of the closed loop characteristic equation, right? So suppose, can I have a branch from -4 starting like this and going like this? I cannot in this current scenario. Why not? Because I am going from the real axis to a value which is going to be a complex number, right? And since we are dealing with real valued real polynomials, that is polynomials with real coefficients, right? If I have a complex root, a conjugate also must be a root, right? So when I do not have a repeating pole at -4, here you see that the multiplicity of a root at -4 is 1, right? I have only one open loop pole at -4, right? So when the multiplicity is 1, then I cannot have a branch like this, right? Because I cannot have two branches starting from the same open loop pole. I can have only one branch of the root locus starting from one open loop pole. That's all I can have, right? So that rules out all this, I would say, evolution in the complex plane, right? So I have only two options. Either it can go on the real axis to the left or to the right. Why should it go to the right? Because of the angle condition, okay? You can check yourself as for homework that, from -4, if you write down the angle condition, it will so turn out that only for points, in fact, between -4 and +1, you will have the angle condition to be satisfied, okay? You cannot go to the right. See, for example, let us say I have one test point. Since we are discussing it, let's say, I take my test point ST to be this. What will be the values of θ1 and θ2 for this? Can you tell me? We just wrote it up, above, right? θ1 will be 180. θ2 also will be 180. So then the sum is going to be -360. Is -360 an odd multiple of pi? No. Alright? Gone. So that's why this will not be, this would not be I cannot have the branch going to the left from -4. On the other hand, you take a test point somewhere here. What would be θ1 and θ2? θ1 would be 0, θ2 would be 180. So you see that the angle condition is satisfied. Correct? Is it clear? How the two branches come off like this. right?